Welcome back. Today we're starting our new unit into atomic structure, where today's lesson we are looking at the particles in the atom and the nucleus, with our lesson objective to understand the properties of subatomic particles of an element, including naming, mass and charge conventions for elements and isotopes. We discussed right back in the very first lesson that in chemistry a lot we've got to reconstruct our models. So we teach one thing that's a limited model that you can understand with the certain amount of information you have at that point. Then you get to a point where you want to make the knowledge more accurate. So you make it more advanced and you make it more complex to more accurately represent the nature. And you keep doing that until we can sort of represent the reality through the models as best we can, while still having the purpose of having a model, which is to make it simple and easily accessible and communicable. So we're doing that in this unit. We're going to look at how we construct the atom, how we draw the atom, and how we interpret the atom, specifically with the electrons. The good news is that our understanding of the nucleus stays pretty much the same as it already is, and today's lesson is just going to be a bit of a recap of what we understand the nucleus to exist as. But in the next lesson, when we look at electrons, we're going to totally reconceptualize how we understand the electron. There are the learning outcomes that we're going to be addressing for this lesson. So let's begin at the start. This is from the very first lesson, this is the slide I showed you, where we have pictures of how we understand the atom to exist at. Now this is a very primitive model, and let's be honest, it's a very inaccurate model, especially with the electrons. The nucleus is pretty good for what we want to understand the atom as. The nucleus we're going to keep the same as very tightly packed positive protons, neutral neutrons. The electrons, however, they do exist in these fixed energy levels as we've talked about previously, but it's a lot more complicated than that. But let's start simple. Let's recap what we know about the atom. We have protons in the nucleus with a +1 charge and a relative mass of 1. We have neutrons in the nucleus with a 0 charge, but also a relative mass of 1. We now understand pretty in depth what this idea of relative mass is. If you want to recap on that, back to the first lesson, it will be there waiting. Now our electron orbiting the nucleus, -1 charge. We said last time it has a relative mass of 0, but we can be more accurate than that. Really, it's got this relative mass of 1/1840th the mass of the neutron and the proton. So very, very negligible when we're considering the relative mass of an atom. But if we want to be accurate, we've got to say that it still does have a very, 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 very small mass there. This is also a slide we've seen before. When we've got an element on a periodic table, we can determine the number of protons with the atomic number, which will be the smaller number. The number of protons is unique to any given element. The number of neutrons can change, you can have different isotopes. The number of electrons can change, you can have different ions. But if you change the number of protons, you will fundamentally change what that element is. So the number of protons, the atomic number, is fixed for any given element. Then we have the mass number, which is the bigger number. This is the number of protons and neutrons together, because they're the only two ones really contributing to the mass of the atom. And we said we can get the number of neutrons if we get this mass number and we subtract the atomic number from it. Then we introduce this idea of isotopes, because a lot of periodic tables report the mass with these decimal places, but you can't have fractions or parts of protons or neutrons. So this decimal sort of gives us a weighted average of all the different isotopes that can exist for a given element. And we talked about how to discuss that, how to calculate that pretty in depth back in our first video of this whole series. But that was the idea of isotopes, where you can have atoms with a different number of neutrons, but it's still going to have the same number of protons. And the abundance these isotopes exist in depends on how stable that particular isotope is. So let's draw some pictures to illustrate what we mean by that. We got 3 isotopes of hydrogen that we know. We have protium, which has a mass number of 1, deuterium, which has a mass number of 2, and tritium, which has a mass number of 3. Now all hydrogen has an atomic number of 1. We know that because it is number 1 on the periodic table. We just get that number off of the periodic table. So we could draw that. We could draw our protium very simply with 1 proton. I'm going to do a positive charge for the proton. It has a mass number of 1, so it's going to have no neutrons, because if you subtract the mass number from the atomic number, you end up with 0. So it's just got 1 proton, and it's got 1 negative electron. I'll do an E for an electron for now. We're going to talk about how we know this in just a second. Secondly, we have our deuterium. Deuterium, we still have one proton because it's still a type of hydrogen. However, now if we subtract the mass number, if we subtract the atomic number from the mass number, we end up with 1. So that means there's one neutral neutron. I'm going to do no sign on there because it's neutral. And we still have one electron. Finally, our tritium, we have one proton, it's still an isotope of hydrogen. But if we subtract 3 from 1, we get 2. So we have 2 neutral neutrons in there with 1 electron around like that. So where did I get these numbers of electrons from? In a neutral atom is neutral because it has no overall charge. So if it has no overall charge, it means the negative charge in the element has to be the same as the positive charge in the element. So in a neutral element or a neutral atom, you can get the number of electrons because it's going to be the same as the number of protons. That's because it has to be neutral. And if you have the same number of positive charge, the same number of negative charge, you're going to end up with a neutral atom. So that's how we determine that. However, if we don't have the same number of electrons, we've got 2 types of ions that we can form. We have what's called a cation, where we have more protons than electrons. If it has more positive protons, it's going to have a positive charge. Therefore, it has lost electrons. Conversely, we can have a negative ion, which is called an anion, where we have more electrons than the protons. So it's got more negative charge than the positive charge. Therefore, it has gained electrons. Now we talk about ions relative to gaining or losing electrons because we just said 2 minutes ago that the number of protons has to be consistent. Otherwise, if you change the number of protons, you've changed the element. So the ions are formed not by gaining or losing protons, but by gaining or losing the electrons. Now we got 2, we got cation. You can remember the cation is positive because it has a T in it, and a T sort of looks like a positive sign. Positive. Anion, you can remember it's called an anion because it has an N. N stands for negative. Positive cations, negative anions. Why do atoms gain or lose electrons? Now we're going to talk about this in depth in the next video, but just to very, very briefly touch on it now, they want to have a full valence shell. It's called the octet rule. They want to have 8 electrons in the outermost shell. They want that because that happens to be a stable configuration. And then, all of chemistry, all of matter and life is just things wanting to exist with the lowest energy possible for the context that it's in. So these atoms form ions because it'll make a lower energy conformation where they've got a full valence electron shell, and it will give a stable configuration. We're going to go really in depth on that in the next lesson. All right, let's do some examples. Determining the subatomic particles in a given species, let's say. How many protons, neutrons, and electrons are in the following? We have a silicon atom. We have a sulfur anion. How would we determine the number of subatomic particles? Well, we've got to use what we know about the mass number, the atomic number, and what the information given on the periodic table says. So for the first one, we're given silicon has a mass number of 28. The silicon atomic number we can get from the periodic table, which will be 14. Straight away, the atomic number is telling us how many protons. So we have 14 protons because the atomic number is simply the number of protons. And that's what makes a silicon atom, is having this 14 protons. Next, we can get the number of neutrons. The number of neutrons is equal to the mass number minus the atomic number. So we get the mass number of 28, we minus 14 from that, we're going to end up with 14 neutrons. We can double check our maths there because 14 plus 14 equals 28. What about the number of electrons? Well, this silicon atom here does not have an overall charge, so the number of the positive things has to be the same as the number of the negative things. We have 14 positive things, we're going to have 14 negative things. So if we got 14 protons, we got 14 electrons. Cool. So we can get a fair bit of information out of just a few numbers and a symbol. What about if we're given an ion? We have a sulfur anion with a mass number of 34. Now, let's talk about the number of protons first. We're going to get that from the periodic table. It's got an atomic number of 16. I just read that off of the periodic table. That means we're going to have 16 positive protons. Mass number, we go that minus that, which, if I do this in my head, I really hope that equals 18 neutrons. Yeah, pretty sure about that. Now the number of electrons. Well, unlike this one, which was a neutral element, over here we have a 2- ion. We'll talk about why it makes a 2- ion as opposed to a 1- or a 3- ion in the next video. But for now, I'm just telling you that it has a 2-. Well, if we have 16 protons, if we had 16 electrons, we would have an equal amount of charge, so we would have no charge. But we've got a 2- charge. So that means we have 2 extra negative charge, then we do the positive charge. The negative charge comes from the electrons, so we're going to have 2 extra electrons to give that an overall charge of 2-. So we can determine the number of protons by the atomic number of neutrons by the mass number minus the atomic number, and the number of electrons by looking at the charge and considering how many protons and electrons it would need to have that charge that it's given. Next one. What about if we're given, determine the symbol for the following? This time you're given the subatomic particles, and we've got to determine what the symbol is. So we've got 19 protons, 22 neutrons, and 18 electrons. Let me collate my information. 19 protons, how many neutrons? 22 neutrons and 18 electrons. I'm getting a bit high there. 18 electrons. Okay, so the first thing we can look at is the number of protons, because the number of protons will tell us what element it is, because the number of protons is fixed for any given element. It's unique to that element. So I look up atomic number of 19 and I end up with a potassium. So we're going to have a K. That's a wonky looking K. Let's try that again. We'll have a K like that. So it's some sort of potassium species. Next, and I'll do a little 19 there because I'll put my atomic number there. Next, we can get the mass number. We know the atom, the only mass is from the protons and the neutrons. So we have to add them together. If I add them together, I will get a mass of 41. 19 plus 22 is 41. I hope. Now let's look at the number of electrons. If we had the same number of protons and the same number of electrons, we would have the same positive charge and the same negative charge, and it would be neutral. But we've got 1 extra proton, then we do the electron. So we're going to have a single plus, because it's got 1 extra bit of positive charge than it does negative charge. So we end up with a symbol like that. Last kind of question that we might get on this kind of thing is determining the number of neutrons in each isotope. This is an example that we looked at from the very first lesson we had, the 2 isotopes, common isotopes of uranium, uranium-235 and uranium-238. So if we've got 235 uranium, 238, not 288, 238. 238 uranium. We can get the number of neutrons in this case by just subtracting the mass number from the atomic number. On my periodic table, uranium has an atomic number of 92. So in both of these instances, we get the mass number, 235 minus 92. That's going to give me 143 neutrons for that isotope. And then 238 minus 92 gives me 146 neutrons for that isotope. So we can determine the subatomic particles given the symbol, we can determine the symbol given the subatomic particles, and we can determine the number of neutrons when given 2 isotopes of the same atom. Okay. Question. How was the charge determined? How did they determine that they had a positive charge for the protons and a negative charge for the electrons and a neutral charge for the neutrons? Well, what they did is they exposed them to an electric field, and then based on their movement, they could infer what the charge of the particle had to be. What do I mean by that? Yeah, by showing how they behave in an electric field. All right, so we know, or we might not know, and I might tell you for the first time, but like charges repel. A negative will repel a negative, a positive will repel a positive. Opposite charges will attract. A positive will attract a negative will attract a positive. This is called the electrostatic force of attraction. So this electrostatic force of attraction is one of the fundamental concepts underlying physics and then consequently underlying all sciences and all of life. And you can test this by getting two magnets. If you put the two negative terminals next to each other, you'll feel a force of repulsion. If you put the two positive terminals next to each other, you'll feel a force of repulsion as well because the like charges repel each other. Conversely, if you put the positive and negative, you will see that they're going to attract each other. Electrostatic attraction of the opposite charges. And that's what we see. If we put an electric field, we put a negative end at one end, a positive end at the other end. And then we can fire our three types of subatomic particles through it, and we will see certain things happening. Let me draw the electric field. We're going to have a negative end. That's my shorthand for negative. Negative sign with VE says negative. At the bottom, we're going to have positive. So we said that like will repel like and opposites will attract. Let's consider what the proton's going to do. So the proton has positive charge. If we consider one proton like that, it's going to have the one down the bottom to show that it's got one proton. If it's just one proton, it's going to have a mass number of 1, so we'll have one proton. If we put this into our electric field and the opposites will attract and we have a positive species here, what we see is that it gets attracted towards the negative terminal like so, and the path of the motion is going to bend towards that. What about if we have a neutron? The neutron has no charge, but it still has a mass of 1. If we have no charge, we don't see anything happening. If it doesn't have a positive or a negative charge, it's not going to be affected by either the negative terminal or the positive terminal. We're just going to see the path of motion stay exactly the same. So we could probably predict what the electron path would look like. And in fact, if you want to pause now and have a prediction of what you think the electron path would look like, you can do that. Our electron has no mass, but a charge of -1. Put a little negative there as well. Now, the negative is going to be attracted towards the positive terminal. However, the electron has such a much smaller mass than any of these two do that we're going to see it have a much more drastic path change than compared to the proton, which is the one that has a significant mass. So to summarize that, observations when you put a subatomic particle in an electric field. The electron beam bends towards the positively charged plate very easily. This infers that it has a negative charge and a very small mass. The proton beam is deflected away from the positively charged plate, or you could say attracted towards the negatively charged plate, that's saying the same thing, but a very comparatively large voltage is needed when compared to the electrons. So if that needs more voltage to do so, then it implies that it's going to be a lot heavier. And if it's being deflected away from the positively charged plate because like charges repel, conversely you could say that it's being attracted towards the negatively charged plate, it infers that it will have a positive charge. So that's what we saw here. The proton, if this electric field is the same for all three of these particles, the proton is much heavier, so it's going to be sort of bent towards the negative much less drastically than the electron, which weighs a lot less. So that's going to be bent in the opposite direction towards the positively charged plate with a lot more severity. And then finally, our neutrons are not deflected by any charge, which implies that they are neutral, they have no charge. Excellent, that concludes today's lesson, our first lesson into the atomic structure unit. What have we done? We've identified and described protons, neutrons, and electrons in terms of their relative charges and relative masses. We've deduced the behavior of beams of protons, neutrons, and electrons in electric fields. We have described the distribution of mass and charge within an atom, deduced the number of protons, neutrons, and electrons present in both atoms and ions given proton and nucleon numbers and charge. And then we also describe the contribution of protons and neutrons to atomic nuclei in terms of proton number and nucleon number, distinguished between isotopes on the basis of different numbers of neutrons present, recognized and used the symbolism of that, where X is the mass number or the nucleon number and Y is the atomic number. As always, if you want to consolidate your learnings, here are some tasks you can undertake. Do one column at a time, starting from the bottom, going upwards. Thanks for your time. See you on the next one.